Single photon avalanche diode, or SPAD, can record the arrival of individual photons. SPADs are a powerful modality for imaging in low light, high speed, and high dynamic range environments. However, previous work has largely focused on monochrome SPAD sensors. In this work, we add color to single photon imaging. Color is an important and often critical component of both machine vision and consumer photography. Our contribution is twofold. First, we notice that a color SPAD array captures a sequence of mosaicked binary images which cannot be easily reconstructed in the presence of scene or camera motion. Inspired by burst photography for conventional cameras, we develop a computational approach that aligns and merges a sequence of mosaicked binary images into a single high-quality intensity image. Second, we analyze and design color filter arrays for single photon burst photography. Instead of a RGB biopattern, we propose the first pseudo-random RGBW color filter array for SPADs. The proposed color filter array features a large fraction of white pixels for boosting low-light performance. Here are some results. First, using a rendered 3D model, we simulate a low-light night scene captured by a moving camera. Due to rapid motion, the image taken by a conventional camera is severely blurred. While conventional burst photography mitigates motion blur, it cannot reconstruct the text in extremely dark and bright regions due to read noise and limited dynamic range. In comparison, single photon burst photography can reconstruct a clear and sharp image while capturing the entire dynamic range. To evaluate real-world performance, we fabricate a prototype color SPAD array with a spatial resolution of 496 by 254 and a frame rate up to 96.8 kilo fps. Here is a mosaicked quanta image sequence captured by the SPAD array. Each frame is 1 bit, with color indicating the corresponding filters. If we naively take a temporal average of the binary frame sequence and apply existing universal demosaicing algorithms, the resulting images are either too noisy or too blurred. Instead, the proposed method performs joint demosaicing and denoising, which creates a clean and sharp image even in the presence of substantial motion. Here we show the same scene but under extremely low light levels. Severe artifacts are seen for the baseline methods, while the proposed method reconstructs a relatively high-quality image. We now show a high dynamic range example. The proposed method can recover the complete dynamic range, which cannot be easily visualized in a single linear image. The linear visualization needs to be scaled by 500x to show the vase in the dark. Nevertheless, with proper tone mapping, it is possible to visualize the entire dynamic range. Besides camera motion, the proposed method is also robust to complex scene motion. This example shows a rotating color wheel. A naive average of this sequence results in washed out colors. The proposed method makes minimal assumptions on scene motion and yet reconstructs an image with clearly separated colors. This example shows a waving feather with complex, non-rigid motion and high-frequency texture. The proposed technique can generate an image with significantly reduced motion blur. By running our method with a sliding temporal window, we can reconstruct videos that recover complex scene motion. In summary, we propose a novel burst imaging algorithm for color single-photon cameras. We built the first color SPAD prototype with pseudo-random RGBW color filters. Experiments demonstrate promising reconstruction results for real-world scenes. We envision that SPAD sensors and their processing pipeline will continue to mature in the upcoming years, and we hope that the computational techniques introduced in this work will inspire future development and interest in single photon imaging.